It's still there, actually. We finished the vase problem here. It's over. We're moving on. Here's a new problem. All right, what does this stuff say? You ready? At the top. What does that say? Okay, these are a couple of points. Right, these are a couple of points. It says when you plug in a 0 into the function, you get 0. When you plug a 2, when you plug a 0 into the function, it's the same as when you plug a 2 into the function, and guess what the y value is? 0, right. So if you plug a 0 in the function, you get 0, and if you plug a 2 into the function, you get 0. So this information was just a couple of points. So maybe we should put them on the graph. All right, check this information out. The next three lines are all about the derivative. And I'm good at this, but you're new at this, but I would look at this middle thing, and what do you think this says? This says that if you plug in a 1, it makes the derivative 0. What does that tell you? If you plug in a 1, it makes the derivative 0.
It's a max or a min.
Okay, good. Well, I think it says that means that x equals 1 is a critical number.
Right.
Now, she went on to say it's a max or a min, but hang on. Keep in mind, a critical number ain't always a max or a min. It usually is, but sometimes it's a neither. I mean, it isn't always. But if it makes the derivative 0, dude, it's a critical number. And it's probably a max or a min. But we're not sure yet until we analyze around that critical number. Like do a first derivative test. Well, guess what? That's kind of what they're doing for me here. If I read this information, I mean, maybe I should draw a number line and see what they're saying here. This number 1 is my critical number. But look what they're saying. When x is less than 1, what are they saying? When x is less than 1, negative. The derivative is negative. Okay, when x is less than 1, the derivative is negative. If the derivative is negative, it's decreasing. The function's decreasing. Thank you. Look what this next line says. When x is greater than 1, the derivative is positive. Well, the derivative's positive. That means the function is increasing. Yes, 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 yes.
That's a min.
So we do have a min. At 1.
At 1.
Dude, I probably can draw this. There is one more piece of, I'm going to go try to draw this. But listen, there is one more piece of information. There's this piece of information. It says that the second derivative is greater than 0. By the way, it doesn't say when, which implies always. Okay, I mean, it didn't say when x is less than 3, or it just, the second derivative is greater than 0. Always, apparently. If the second derivative is greater than 0, what do I know? If the second derivative is positive, the graph is concave up. Thank you, I do know that. That's what that's telling me. It's telling me the graph F, is concave up. Dude, that's what all that stuff says. I think I can draw this graph now. Decreasing, concave up, decreasing, concave up. When you hit 1, you've hit a min. Now, they didn't give me a y value here.
Yeah.
So I don't know how low to go. But when I hit 1, I've hit a min. And then what happens after that? I should increase. I should increase. And by the way, I'm concave up. I'm always concave up. So yeah, I got you. I decrease, I increase, I'm concave up. Looks a hell of a lot like a parabola in a way.
Yep.
It is a parabola.
So that's what all this said.
Wow.
I like these questions. They're not really that hard, I don't think. You just got to learn to read this mathematics. Read these notes. What's it saying? And this is all about. This is the first derivative test. I mean, it's all the good information from a first derivative test. Maybe I'm not good at reading it like this, so I read it like this and put it on a number line so I could understand what it meant, you know? I read this and put it on a number line because I'm more comfortable with my number line.
Yeah.
All right, we're done with that question. tell you about the second derivative test. Okay? That's something different. So, if I'm in 4.4, there is a thing called the second derivative test. But, and whatever. So, this is called the first derivative test. You know how to play it. We've gone over it a million times. When I play the same game using the second derivative, I've called it a concavity test. Don't call it a second derivative test, I said, because there's something else called a second derivative test. Well, here it is. And here's what it is. Let me say what it is. It's a test to determine if your critical numbers are mins or maxes. Okay, now that's kind of funny. Do I already have a test for that?
Yes,
The first derivative test does that for me, doesn't it?
Mm-hmm.
It sure does. The first derivative test is a test that helps me decide if my critical numbers are mins and maxes. So here's another test. Maybe that's why it took me a while to get it out. I feel like I don't really need him. But he's kind of cool. He's got some cool aspects. Here's what it is. It says if x equals c is a critical number, and we know what that means. It means it came out of we used our first derivative, we set it equal to 0, we got our critical numbers. If we find a critical number, then here's what we do. We take that critical number and we plug it into the second derivative. And if the second derivative at that critical number is positive, now wait a minute, hang on. Now, by the way, when the second derivative is positive, doesn't that mean you're concave up?
Right.
And so check this out. If you're concave up, but if you're a critical number, then you live in a concave up environment. If you're a critical number that lives in a concave up environment, you gotta be a min. Thank you. That's what this says. That's how this works. If you take your critical numbers from your first derivative and plug them into the second derivative, the conclusion is if your second derivative is positive, that critical number is a min. And if the second derivative is negative, it's a max. The explanation is how I explained it a second ago. Let me try it on this one. What am I saying here? I'm saying that my critical number, wait a minute, I'm saying my second derivative is less than 0. If my second derivative is negative, it's concave down. But you're a critical number that lives in a concave down environment, you're a max. Yeah. It's very logical again. All this stuff is pretty logical. It's math. So there's the second derivative test. I don't personally use it too often. I got something called the first derivative test.
That's it.
It's like the same.
Yeah.
Well, it's another test to determine whether your critical numbers are mins and maxes. Do we already have a test to determine whether, yes, it's called the first derivative test. So here's another test. I don't use it too often. I got the first derivative test I tend to do, okay? I don't use it too often, but listen, there are times when maybe you don't have the first derivative. Maybe all you got's the second derivative, and so you can use it to determine some stuff. I mean, anyway.
How is that different from the inflection?
Well, inflection points are when the second derivative is 0. This is, which by the way doesn't show up, you know what I mean?
Okay.
But
The second thing is the inflection thing.
yeah, I mean, in a way, I don't even want to talk about inflection points. That maybe confuses the issue here. I mean, this is a test for my critical numbers. My critical numbers come from the first derivative, and it's a funny thing you do. You take your critical numbers and plug them into the second derivative and see if it's positive or negative, and that determines whether they're mins or maxes. And And maybe it seems weird, but I explained why. The explanation of why is good. It's about the concavity. The concavity tells you whether you're a min or a max, kind of. That's the idea, right? The idea was, if this is concave up, but you're a critical number, that's the thing. C is a critical number. So you're not just concave up, but you're a critical number in a concave up environment. A critical number in a concave up environment has to be a min. That was the idea. It's cool. Yeah. I don't know. We'll see what the home. Anyway, that's it. The homework. Might make you think about that somehow. You know what? Let's do this other thing here, and then we'll quit today. Are you ready for this? I feel like I'm. Where am I? I feel like I've done 4-1, 4-3, and 4-4. I mean that's kind of where I am. So can you catch up to me, please? So catch up to me. I mean that's where I am. And now I might do this little 4-2 I skipped. You ready? Let's talk about 4-2. It's a little unrelated. It's this funny little theorem. Check this out. In 4-2, there's this thing called Rolle's theorem. Don't put words in my mouth. Rolle's theorem. Let's see. I'm going to read it to you. I'm not going to read it to you. I'm going to write it up here. Here's what it says. It says let f has to be continuous. Let f be continuous. So we got a function that's continuous on a closed interval a, b. They also want f to be differentiable. We know what it means to be non-differentiable. So we want it to be differentiable on the open interval a, b. So those are the two requirements for Rolle's theorem. And then here's what Rolle's theorem guarantees. If f of a equals f of b, then there is, can you read my writing? Then there is at least one point, or one number, shouldn't call it a point, one number c in AB, in the interval AB, such that f prime of c equals 0. Now, what do you think about Rolle's theorem? First of all, well, this is very mathy. This is how math, if you're a math major, you got to get used to this. I mean, I was a math major, but when I teach calculus, I don't usually teach a lot of theorems and write a lot of theorems. I kind of teach you how to do the problems. You know, the theorems are kind of behind the scenes sometimes. Maybe I feel like most of my students are engineers and they want to solve problems. They don't want to really get into the math theory, you know? But the truth is, it's all good for us. It's all good. It's all good. But it's a little hard to read math. It takes some getting used to. I mean, I know what this says. I've been reading it and thinking about it a little bit. It's kind of funny. You know, here's what it says. First of all, we're working on some interval from A to B. So here's an A and here's a B. My function has to be continuous from A to B. So it's got to be continuous. Oops. The other funny thing, and I just screwed that up, it's got to be continuous. It's also got to be differentiable from A to B. But they leave out the endpoints for some interesting reason. A little math technicality there. But it's got to be differentiable. You know what that means. It probably can't have any sharp points. You follow me? means more than that, but that's kind of, I'm summarizing. It shouldn't have any sharp points, because sharp point would be non-differentiable. Okay, so it's got to be continuous, it's got to be differentiable, and then what else has to happen? Oh, if f of a equals f of b, which means those y values line up, and I didn't do a good job of that. Hang on, I didn't do a good job of that. If f of a equals f of b, that's a little better job. F of a, the y value equals f of b. You with me? Then it says there is at least one number c in AB, so somewhere in here there's a c such that the derivative at c is 0. Meaning at that place c, the derivative is 0, or the slope is 0 at c. Does it look like that happens?
So it's a maximum.
It does look like that happens.
So it's a critical point.
So c is a critical number.
Right.
So they're guaranteeing me a critical number if I got to meet all these requirements. What are the requirements? It has to be continuous from A to B, including the endpoints. It has to be differentiable from A to B, not including the endpoints. It has to, f of A has to equal f of B. And then I'm guaranteed to have a critical number. You're right, where the derivative is 0. Somewhere in AB. That's what it says. Not sure how useful that is, but that's what it says. Let's do another one. Okay, so also in 4.2, after you learn Rolle's theorem, and that's what it says, that's fun. I just erased my cool picture, sorry. I should have left that picture up there, maybe I will. Hang on, what was the cool picture? The cool picture was an A, a B, these points had to line up the same, and then they're guaranteed to be a C in there where the derivative is 0, right? That's kind of a picture of Rolle's theorem. Okay, check this out. Here's another theorem in 4.2. It's kind of, after you learn that one, then this one sort of is the mean value theorem. The mean value theorem. All right, what does it say? I think it says f has to be continuous. The f is continuous on AB again. I think it says f is differentiable on AB again, and this time they say, what do they say? I'm going to read it. What do they say this time? Then there does exist a number C. They don't have this other requirement. They say then there is a number C. There exists a number C in AB. There exists this number C in AB where f prime of C equals f of B minus f of A over B minus A. Do you know what the hell that's saying? Here's a picture of Rolle's theorem. Let's see if I can draw a picture of the mean value theorem. All right, what do I got to have? I got to have a function that's continuous. Here, let's start. I need an A and a B. I need an A and a B. Those are x values. I'm working on an interval. The function has to be continuous from A to B. Okay. Function's continuous. It has to be differentiable, so no sharp points or you know, it's got to be continuous, so no holes, no asymptotes, no breaks, right? It's got to be continuous, and it's got to be differentiable, so no sharp points or weird things. So I think I'm pretty good there. And then what does it say? First of all, what does this say? Can you, what is that? Does that look like anything to you? What does that look like? Here, by the way, this is A. Here's f of A, right? You guys, it's that y value. If this is B, then here's f of B. You know, it's a y value. What is this? Yeah, isn't this just a slope? This is a y value minus a y value over an x minus an x, isn't it? Okay, so hang on. Ignore the derivative for just a second. This is just a y minus y over x minus x. This is just the slope between those 2 points. So what are they saying? If you calculate the slope between those 2 points, they're saying, here's what they're saying, there is a number c such that somewhere the tangent line has that slope. There is a number c living in there somewhere where the tangent line has that slope. Let's look over here and see if that's right. They're saying there's a number c, there is a place c where the tangent line has that dude's slope. Like maybe here. Look. Where the tangent line matches that slope. You following me? There is guaranteed to be a number c in that interval where the tangent line has the slope of those endpoints. Hey, isn't that profound? Yeah, I know. Sorry, doesn't seem too profound. It almost seems obvious, but maybe it's not obvious. It kind of is after you explain it and draw it. How useful is it? I'm not sure. What I read is it says, these theorems, you know, what I read was, after you learn these theorems, you can read the book, it's kind of interesting. It says, these theorems aren't all that useful by themselves, but they're useful proving other theorems. Knowing these help you prove higher other theorems. And by the way, that's kind of what math majors do. They prove theorems. I mean, you're sitting in a calculus class, we're doing a lot of math, but we're not proving a lot of theorems, are we? Yeah. Do you want to? No. You like it the way it is? You like doing math, bro?
I don't mind. I like both.
Yeah, both. I mean, right. Both would be better. I don't, yeah, anyway. That's what it says. Now here's what I did. In 4.2, I assigned a few problems. And what you're usually doing, what the problems usually are doing, is they're saying, make sure that if you can apply the mean value theorem, then please do it. Now hang on, so that means you got to sort of check to see if you can apply it. How do you check to see if you can apply the mean value theorem? Well, you got to make sure your function is continuous. You got to make sure it looks like it's differentiable, and then you can apply the theorem. And then what they usually say by applying the theorem is find that number c. So then you probably should do these calculations, and you should probably do the derivative, but then you're looking for when the derivative equals this. You're looking for the c value when the derivative equals this. So you could try a few problems. Here, I assigned a few. I didn't assign many. They weren't in your original homework list, but here they are. 4.2, 9, 13, 21. Those are Rolle's theorems. That's this one. And then the mean value theorem is 41, 43, and 48. So you could try those, and maybe I could help you with them if you're having trouble. 59, I also decided I thought looked good. And maybe 68 for a challenge. And maybe, anyway, I'll let you try those. All right, can I teach you some other stuff? Sure. Oh, boy. All right, let me teach you some other stuff. Here's what I want to tell you. So 4.1, 4.3, and 4.4. That's, you know, I presented those topics, and to me that flows. That flows real good. The 4.2 is a little bit different, okay? It's the Rolle's theorem and the mean value theorem. I don't know if it doesn't necessarily tie all in with all those great ideas, okay? So the 4.2 is just a little different, I thought. Okay, so then this flows good. Okay, what comes next? Well, 4.5 is kind of interesting, but then 4.6 is a summary of everything before this. So there's really nothing new to teach you in 4.6. It's a summary of all the crap you learned prior. Okay? So there is some stuff coming after 4.6. There's some word problems and some other things after 4.6. So we'll get to some other ideas. But so in a way, the first half of this chapter is done. I just sort of need to talk about 4.5. Okay, what's 4.5? They're called limits at infinity. So we jump back and do some limits again. Is that what it's called? What's it called? Yeah, limits at infinity. That's exactly what it's called. And so here we are in 4.5. We look at some limits again. See, we did limits. We didn't ever do too many limits. Maybe I hinted once or twice, but I never did too many limits that went to infinity. X is going to infinity. So this is the limit of this function as x goes to infinity. They sort of saved them for section 4.5 for some reason. You'll see why in a second. So I made up this problem. What's the limit as x goes to infinity? Now, do you remember the first rule I taught you of limits? What do you do here? Plug it in. Yeah, thank you. That's the first step. Plug it in. Now, it's a little weird plugging in infinity because it's not a number exactly, but you can try to imagine it. If you plug in infinity and multiply it by 2, don't you think that's infinity?
Yeah.
Okay, good. What if you subtract 3? Sure?
Still infinity.
Yeah.
Yeah, thank you. Infinity minus 3 is still infinity. Okay, cool. So the numerator is infinity. All right, in the denominator, infinity times 5, I think that's infinity. And when you add 8, it's pretty insignificant. It's infinity. So I have infinity over infinity. And infinity over infinity is called an indeterminate situation. From our earlier study of limits, do you remember an indeterminate situation we would often run into? It was 0 over 0 often.
Yeah.
That was indeterminate, and what we would do is try to go figure it out.
Right.
Well, so infinity over infinity is called indeterminate. You can't, without a little further analysis, you can't really just say what that is. Infinity over infinity requires some investigation. It's called indeterminate. All right, I'll tell you what, do me a favor. I know the answer to this. Do you know the answer to this? What'd you say? How do you know that?
Because there's rules. That's how you
Yeah, but what made, that's good, but what made you think of that? Old pre-calculus ideas? All right, anyway. So let's do this. Can we plug in 1,000? Let's just, because we're going to infinity. 1,000's pretty close, right? 1,000 ain't close. 1,000,000? Let's try 1,000,000. That's pretty close to infinity. No, it ain't. No, but you can plug in 1,000. You could probably plug in 10. You could probably plug in 100 and see the point. Watch. I'm trying to head toward infinity. I want to plug in something and see if I can guess what's going on. If I plug in 1,000, I want to watch what happens. It's interesting, kind of. You get 2,000 minus 3. What's 2,000 minus 3? 1997? Over 5,000 plus 8. So that's 5,008. Somebody make that a decimal, please.
.4 or .398.
0.398, that's what I prefer. Thank you. Or, yeah. So he said 0.4. Hold on. Let's plug in, all right, let's plug in 1,000,000. Let's plug in 1,000,000. So that's 2,000,000 minus 3. What's 2,000,000 minus 3? 1,999,997. All over 5,000,000 plus 8. What's 5,000,000 plus 8? 5,000,008. And if you divide that, what is that one? By the way, can you just say it's roughly a 2,000,000 over a 5,000,000? You can, right? Roughly? And if it's roughly a 2,000,000 over a 5,000,000, then it's roughly a 0.4, right? What did your calculator say? 0.3999. 9876. Okay, thank you. Anyway, dude, it's a 0.4. You're totally right. It's a 0.4. You know what? Here's the deal. When you're headed toward infinity, you guys, you're on a graph and you're headed toward infinity, this question is really, here's what this question really is. What's the horizontal asymptote? That's really what this question is. Now, let's go back to pre-calculus. Because when you're headed toward infinity, really the question is, if there is one, what's the horizontal asymptote? That's really what the question is. If there is one, what's the horizontal asymptote? And do you remember pre-calculus? Do you remember your rules of horizontal asymptotes? Okay, I'll remind you. The rules of horizontal asymptotes was when the degrees are the same, when the degree of the numerator is the same as the degree of the denominator, then it's the ratio of the leading coefficients, 2/5. The horizontal asymptote is 2/5. 2/5 is 0.4. So at 0.4, there's a horizontal asymptote. And what we just discovered by plugging in some points is that when x heads toward infinity, it's getting closer and closer to 0.4. So as x heads toward infinity, the y value is 0.4. It approaches 0.4. It never gets there. But the answer to this limit is 0.4, or 2/5 of 0.4. The answer to this limit is 2/5. Okay, but it's also the answer to this question. Forget limits for a second. Hey man, what's the horizontal asymptote of this thing? 2/5.
That's it.
Well, so these limits that go to infinity are really questions about the horizontal asymptote. And I'm trying to, did I make sense of that? Because when you head toward infinity, you're going way the hell out there. And if you're going to approach something, it's going to be an asymptote. I don't know, look at this picture. What's the limit as x goes to infinity? As x goes to infinity, what's this function doing? What's the y value, please? Infinity. Okay, here's another picture. As x goes to infinity, what's the y value, please? Negative infinity. Okay, so here's another picture. As x goes to infinity, what is the function doing? Approaching a y value of 0. Good. In this case, there is a horizontal asymptote, and where is it?
0.
At 0. At these two cases, there is no horizontal asymptote. When x goes to infinity, it goes to positive infinity, or in this case, when x goes to infinity, it goes to negative infinity. There is no horizontal asymptote. But when there is a horizontal asymptote, then when x goes to infinity, that's what it approaches. This one's 0. This one's 2/5, or 0.4. What's my point? My point is, when you go to 4-5, you learn about these new things called limits. But I'm trying to tell you, it's just it's a calculus way of discussing horizontal asymptotes. I mean, in an algebra class, somebody can tell you the rules of horizontal asymptotes. Nobody usually asks you this question in an algebra class, but this question is asking, what's the horizontal asymptote if there is one? That's what it's asking. And so you're comparing degrees of the numerator to degrees of the denominator. Here, let's do another one. What's this? All right. I mean, there's different ways. Anyway, what have I taught you? Step 1 of doing limits? Plug it in. Okay, let's see what we get. Infinity squared. Infinity. Times 5. Infinity. Minus 8 times infinity. It's still big old damn infinity. What about plus 12? I mean, see, what you learn is that all this shit is pretty insignificant. I mean, when infinity's being squared, that totally takes precedence. The rest of this is gone. It doesn't matter. It's the leading coefficient, leading power that really matters. It's infinity squared. So anyway, it's infinity. All right, what about the denominator? Infinity. Wait a minute. What about when you add 117,000? All right, it's still infinity. All right, cool. So anyway, I tried plugging in infinity, and I got infinity over infinity. Infinity over infinity is indeterminate. I'm not really supposed to know what that is. But the difference is, on this one, they're kind of the same size infinities because they were both degree 1.
Right.
And so it was the ratio of the 2 to 5 that was the answer.
Right.
On this one, they're kind of not the same size infinity. If you remember, this dude was infinity squared. That really kicks poor old infinity's butt.
Yeah.
Sorry for the violent metaphor. But infinity squared kicks infinity's butt. So in the race to who's going to infinity, that numerator is a bigger, badder infinity than that infinity. So now what the hell's the answer? If your numerator blows up and goes to infinity quicker than your denominator, I think the whole fraction goes to... If the numerator blows up to infinity, like I said, this is bad math. And if the professors at UF saw me do this, they'd kill me. You ready? I'm saying this is all insignificant. All you really got is 5 times infinity squared. That damn 5 is insignificant. Over an infinity. So you have infinity squared over infinity. Can you just cancel one of those damn infinities? Don't tell anybody I did that. Is this on video? Holy shit. If you cancel one of those infinities, what's the answer? Infinity. So what does this do? What's the answer to this? Infinity. Yeah. It's this picture. It's sort of this picture. It goes to infinity. The numerator beats the denominator, and that takes it to infinity. Let's have this discussion. Let's tie it to the horizontal asymptote discussion. That's what I'm trying to do. Do you remember the horizontal asymptote rules when your numerator has a higher degree than your denominator? Do you remember? Yeah, it ain't a horizontal asymptote. When the numerator has a higher degree, it wasn't a horizontal asymptote, it was a slanted asymptote. He called it an oblique asymptote. He's right. And it was slanted. If you have a slanted asymptote and you approach it, then where are you headed toward? Infinity. I mean, you're not headed toward a y value. If you have a slanted asymptote, you're not headed toward a constant y value. You're headed toward infinity. This answer is infinity. And I would say it's because the numerator has a higher degree than the denominator. That's it. That's what I'm trying to get down to. Sorry it takes me so long to talk. Here, what about this one? The limit as x goes to infinity of this one. 5x 5x squared plus 2 over x cubed. No. 5x squared plus 2 million. That's more than 2 million. 20 trillion. 5x squared plus 20 trillion over x cubed. All right, step 1 of doing limits. Plug it in. Okay, here we go. We plug it in. Infinity squared times 5. Infinity plus 20 trillion. That's still just infinity. In fact, the 20 trillion is insignificant. So it's infinity over infinity cubed. That's infinity. So it's infinity over infinity. That's sort of technically indeterminate. But do you remember the rules of horizontal asymptotes? Well, forget that a second. Forget that. Which infinity kicks which infinity's butt? Thank you. Infinity cubed beats infinity squared. It really does. Even if you add 20 trillion to it. It's insignificant. Okay, it's insignificant. So infinity cubed beats infinity squared. When you have a fraction whose denominator blows up more than the numerator, What's the deal? What's happening with a fraction whose denominator is huge?
Zero.
It goes to zero. A fraction whose denominator is huge goes to zero. This is zero. You following me? The denominator wins. The answer is zero. Do you remember the rules of horizontal asymptotes? The rules of horizontal asymptotes, do you remember the rules? When the degree of the numerator was less than the degree of the denominator, do you remember the rules?
Yeah, y equals 0.
You had a horizontal asymptote at y equals 0.
Yeah.
Yeah. So I did all three examples for you. When the degree of the numerator is less than the degree of the denominator, the answer is 0. That's the horizontal asymptote. It's also the answer to this limit. It's 0. When they have the same degree, the answer is the 2/5. That's the answer to the limit. It's also the horizontal asymptote. When the numerator has a higher degree, there ain't no horizontal asymptote, and this thing goes to infinity. That's the story. That's the three aspects of the story, kind of comparing the degrees of the numerator and denominator and doing these limits that go to infinity. It's really tied directly to the horizontal asymptote story.
So is that graph on the third one on the left, the one for the...
Yeah, thank you. This is headed towards 0, so I could draw a picture of it, but he found one over there, right? Just something that heads towards 0, right? Right. I mean, it could be heading towards 0 from the underside. I don't know about the specifics here, but it's headed towards 0. Yeah, eventually. Yes.
And could you have negative infinity if the...
So I'm headed toward infinity. They do these questions, and they do make you head toward negative infinity. But when you head toward negative infinity, the same rules sort of apply. The horizontal asymptote story.
Okay.
It's still the horizontal asymptote story.
Okay.
Kind of comparing the degree of the numerator and degree of the denominator. So yeah, you might have to watch the sign. Right. All right, I'm going to quit today. Thank you guys for listening. Where am I? Oh, look. So if I did 4, 5, then that means I'm done with 4, 5, and so you can do 4, 6. I mean, I'm done with 4, 6. 4, 6 is nothing new. 4, 6 is a summary. Oh, and by the way, we did 4, 2. So, good luck. I mean, no, I would love to pause and help you with some homework Monday. Anywhere in here. At some point, we'll move into 4, 7, do some word problems. Max, min word problems. That's what's coming next.